Recording in progress.
Hello, good morning, Poki.
Good morning, everybody, especially Trio. Thank you very much for such kind of very nice invitation. Hopefully, I can share my experience with all the participants, especially for the students.
Okay.
So we are waiting for 10 o'clock.
Yes, just 2 minutes again.
Yeah,
But
no worries.
9 o'clock in Indonesia.
Ah, yes, yes. No worries. There is only 1 hour between us. Not far away. So may I share my screen first?
Yes, you can prepare, Prof.
Oh. Usually we don't use Zoom, so I have no. Oh, okay, here. Wait a moment. This one. Is it good?
Yes, very good.
Okay, hopefully.
Okay, ladies and gentlemen, good morning. My name is Infal Syafalni. Today I will be the moderator for the lecturer of Professor Poki. Maybe at the first, Prof. Tireo will have some welcome speech. For Prof. Trio, we welcome you to take the stage.
Okay, thank you, Pak Infal. So I would like to welcome Professor Poki. Now he's adjunct professor at School of Electrical Engineering in ITB. So we hope by this event he can share his research and experience in very hot topics, analog using FPGA. We know that designing analog is very challenging. It's very difficult for us to deal with analog circuit. However, there is new approach, which is we can approach it by digital designs.
Yes.
So it's more easy for us to doing approach. So hopefully by listening this lecture, we can have an idea, and learn from Professor Poki, how to design this analog circuit. And because we cannot avoid the analog, because our work is analog. Okay, thank you for your participate in this event, and we hope we can do more event in collaboration with NTUST, of course, and also I think we also arrange many other program with NTUST, such as double degree, student sending students to NTUST, and hopefully you can join this program. Next week we also have a lecture regarding the 5G, Professor Ari. Thank you very much. Enjoy the webinar. Thank you.
Thank you very much, Professor Trio, for the welcome speech. Now I will read the biography of Professor Poki Chen. Professor Poki Chen received the Bachelor, Master, and PhD degrees in Electrical Engineering Department from National Taiwan University, NTU Taipei, Taiwan. During 1998 to 2001, and 2001 to 2006, and 2006 and 2011. He was a lecturer, an assistant professor, and associate professor correspondingly in Electronic Engineering Department of National Taiwan University of Science and Technology, NTUST. He is now a professor in Electronic and Computer Engineering Department of NTUST. Since 2010-2013, he was selected as the director of System on Chip Research Center, Business Incubation Center, NTUST. Since 2014 to 2017, he served as the chairperson for ECE department. Currently, he serves as Dean, Office of Industry Academia Collaborations. Since 2011, he is an associate editor for IEEE transactions on very large scale integration, IEEE TVLSI, and also IEEE Access. He is also the editorial board of International Scholarly Research Network, Electronics. He is the organizer of many top conferences. I think this is such as SOCC, LSI DAT, EFEEC, and many others. And his research interest is analog and mixed signal integrated circuits and systems, with special interest focus on time domain signal processing circuits, including a time domain smart temperature sensor, time to digital converter, digital pulse generator, digital pulse width modulator, and duty cycle corrector. And he is also interested in creating innovative analog applications for FPGA platforms. And now we welcome Professor Poki to give some inspiration for us. Please, student, take attention. Please welcome Professor Poki.
Thank you. Thank you both for such kind of very good, even more than good enough introductions. It's my much honor and pleasure to deliver the speech to the most outstanding students in Indonesia. Am I right? Yeah. So hopefully after my talk, there will be quite a few students interested in our research topics. Look into the future. I hope we can have even better collaboration. Yeah, I mean, between NTUST and ITB. So, ladies and gentlemen, good morning. Yeah, even though there is only 1 hour in between us, our morning is usually the same for yours. Selamat pagi.
Selamat pagi.
Selamat pagi, Pak Poki.
Yeah. Okay, let me go further. Here is some kind of very brief introduction as already introduced by both gentlemen. Allow me to go further. This is my office, my email, and my website for you to refer. And for today's talk, because I have only 1 hour, so I need to speed up. Later, I will skip some of the not so important content. However, these are the guidelines for my today's talk. From the very beginning, I would like to tell you something about the motivation, because it is, as Professor Trio said, sometimes it is harder to design circuit in analog domain. Anyway, it depends on who you are. If you are analog IC designers, I think it will be harder for you to design some kind of digital circuit, vice versa. Yeah. for digital IC designers, I meant any kind of analog function, have some kind of brief discussion about the motivation of myself and my for analog. You can see, usually for the design nowadays, we hope we can achieve such kind of very good, or allow me to maybe, okay, it will be even better. Yeah, we would like to achieve something like low cost, high resolution, wide measurement range, and very low sensitivity to process voltage and temperature variations. Sometimes it looks like something very similar to Mission Impossible, but as students or designers, you need to make impossible become possible. That is what we are required to. Anyway, we have many kind of analog applications. For example, time to digital converter to measure the width of the timing signal. If you would like to compete with all the others, I mean around the globe, then the resolution had better be around picoseconds. I'm talking about -12 power of 10, -12. Wow, it is really small, right? For process, I think you guys already know. Nowadays, we talk about nanometers. That is the -9 power of 10. But for TDC, sorry, nanosecond resolution means nothing for today's design. You need to go further to enhance the resolution by 3 orders, all the way from nanosecond to picosecond. Otherwise, I don't think your paper, your publication will be accepted. That is the really sad story. Then you can reverse the process to achieve something called digital to time converter. Yeah, we have digital input and then generate the timing signal with width proportional to the digital input. And again, how about the resolution required for nowadays design? Sorry again, picosecond resolution. Otherwise, you cannot compete with all the others. In addition to those TDC, DTC, we have many kind of sensors, and we can also apply FPGA platform to achieve something called DPWM, digital pulse width modulation. Yeah, and for all the others, as you think, as you say, if you are interested, you can try to implement, I cannot say all the analog applications with FPGA platform, but many of them, all right? It depends on your innovation and your ambition. If you would like to make it, you try your very best. I think sooner or later you can make it, but I will tell you the truth. I will tell you all the secrets, how to implement such kind of analog functions with FPGA platform. Usually FPGA is some kind of digital platform, right? How can we implement analog functions with such kind of pure digital platform? From the beginning, you guys may be curious, why? Me and my students would like to apply FPGA for analog design. Yeah, allow me to tell you some truth. If you compare FPGA to ASIC, ASIC means what? You do your own design. Never mind for digital or analog. Yeah, for ASIC, to be honest, it can help you to achieve the best performance as you like. Yeah, it's up to you. I always tell my students, there isn't any performance you cannot achieve. There's only some price, some cost you cannot afford. That's it. So if you would like to achieve, the best performance, I guess you need to pay for it. Pay what? ASIC design. Okay, you need to design your own chips, especially in analog domain. You need to fine tune the device parameters. For example, the width, the length, or even the bias current for all the devices. Yeah, more than often we focus very much on MOSFETs, right? But in addition to transistors, you still need to pay attention to capacitor, resistor, blah, 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 all of them. Yeah, anyway, anyhow, that is what you can achieve with ASIC, right? However, ASIC means what? Very expensive, very expensive. Yesterday, I invited a mentor from Realtek. Realtek, right now, I think that is the best company for Wi-Fi 6. Yeah, in Taiwan, Realtek, I think it gets top 3 ranking. Globally, the mentor told me around 11 for fabless IC design houses. Fabless means they don't produce their own chips, not like Samsung or Intel, yeah, or Micron. They design, fabricate, test all their own chips. But for many of the others, just like Qualcomm, or even Apple, they don't produce any chip by themselves, right? So among such kind of fabless IC design houses, Realtek is already top 11 around the globe. In Taiwan, we have 3 among top 15. Yeah, you can guess MediaTek, the best. Then maybe Novatech, and then Realtek. We have many kind of techs, high techs. Yeah, the mentor told me even for a set of mask, it cost more than 100 million NT dollars divided by 30, sorry, it will equivalent to the US dollars. So do it by yourself, okay? Maybe you need to multiply by 25 or something to make it equivalent to Rupia. Maybe, I have no idea. Anyway, anyhow, wow, it means what? It's a huge money. Yeah, to my guess, I think is around $250 million US dollars, or even more than that. It depends on what kind of process you would like to apply. So ASIC is really expensive. It only makes sense for mass production, but we have many kinds of small to medium scale productions, right? Just like the chips for your car, for your home electronics. I don't think they can produce billions of chips per year. That is too much for home electronics, home appliances. So if you would like to scale down the production, then maybe you need to try the other way. And allow me to show you FPGA is the best among all the possibilities. Why? Because comparatively, it is the cheapest for small scale production. And all the design tools actually are quite mature. And more importantly, you can see here, many of the key analog blocks actually right now are embedded into FPGA platform. What kind of analog blocks you guys can have? For example, ADC, DAC, right? Analog to digital, digital to analog conversion. Not only those, but also phase lock loop, delay locked loops, right? PLL, DL, blah, blah, blah. Many of them. So you can enjoy not only the digital design, but also you can apply such kind of analog blocks to enhance the overall performance of your FPGA platform. And then allow me to show you the most important secret for FPGA analog design. You need to focus on time domain signal. If you would like to process voltage our current signals. Sorry for that. It is totally impossible for FPGA. Maybe it is also impossible for digital IC design, right? If you would like to process any kind of analog signal, please convert into time domain. That's it. That is the first secret I would like to share with all of you. Why not in voltage domain? Not only that, it is impossible to process voltage signal with FPGA directly. Yeah, you can say, hey, I can convert the voltage by ADC into digital signal, right? Into digital output, then you can process the digital signal with your FPGA. Yeah, sure, but you need to pay for it, right? You need to pay the price for ADC. Yeah, usually it is not cheap. So if you would like to process the signal directly, the only possibility is time domain. Okay, you need to convert any kind of signal into time domain. Then we can process it with FPGA. Later, I will have a little bit more discussion about this. Again, not only because we can process time domain signal with FPGA, but there are so many the other reasons. Allow me to show you this. There are too many successful predecessors. Yeah, so it is really hard for you to compete with them. If you are new to such kind of field, how can you compete with all those researchers? They focus on such field for more than 10 or 20 or 30 years. No way, right? You need to find the other way. Not only to keep pace with them. No, you need to go further to turn them down. Yeah, that is the way for success. All right. And it is not so innovative because almost everybody discuss how to process voltage signal to be different, especially you need to think differently, right? So time domain signal or a bit much better for you. And also that for voltage signal, it's hard to digitize because I told you already, you need the help of ADC, right? That is expensive, power consuming, yeah, many of the demerits. And also that for such kind of voltage domain processing, it is expensive. It needs much more power than signal processing in time domain. Yeah. Anyway, anyhow, I cannot only tell you the disadvantages. I need to be honest because I'm an honest man. So I need to point out the best for such kind of voltage domain signal processing. Yeah, usually it can achieve the best accuracy. Why? Because humankind focus on such kind of voltage design for not only many years, for many centuries, yeah, many hundreds of years. So usually we can achieve the best accuracy in voltage domain, but we are humankind, we are not gods. We, for the design, if it is good, it means good enough, no more. Why? The students or the new engineers usually have some kind of over design. Yeah, to be too good to be true, right? Sorry for that. You will simply waste your time and money, especially the money of your company. If you design the circuit to be too good, it means it will be too expensive. Sorry. So for many of the good enough analog applications, actually, we don't need such kind of very good, very excellent accuracy. That's it. So with good enough accuracy, many of them can be designed in time domain. Okay. As I mentioned, you need another way. Yeah. To defeat all the other prior arts. Okay, but what is the difference between innovation and innovative and naive. The same is to think differently, right? But what is the most important difference? For being innovative, you can achieve something good, all right? But for naive, can only achieve nothing, or even put yourself at risk, just like this. If you lose, if you fail for your new design, maybe your companies will get, then sooner or later you will be fired. Okay, if you they wouldn't like to fire you, then maybe the company will go for bankruptcy. It's really no good for the company and yourself, right? So hopefully we can be innovative to find different way for our design, then become the top of the world. That is what I need for my students. Okay. And the other reason is why not to process voltage signal in voltage domain. You need for such kind of digitization, quantization, you need to differentiate the voltage difference between your input and output. Yeah, for example, for ADC, for flash ADC, you need to discriminate in which level. You need to judge which level is closest to your input voltage, right? So you need to compare your input voltage to many of the reference voltages. But how can you do that? How can you do such kind of voltage comparison? You need such kind of voltage comparator, and usually you need to design op-amp, operation amplifier, to achieve it, right? For many of you, I think it is not so easy to design a good enough voltage comparator, especially with op-amps, right? To make the matters even worse is right now, according to process scaling, the size of the transistor becomes smaller and smaller, and you can see what? The supply voltage becomes smaller and smaller and smaller. The same, right? So you can see even with the same resolution, in the past, you have high enough supply voltage, right? So you can differentiate the difference between the levels, the voltage levels, very easily. But according to process scaling, the supply voltage becomes smaller and smaller and smaller. Oh, to the end, how can you differentiate all those voltage references? It's no way, right? Because the difference becomes so small, you cannot see it clearly. To make it even worse, I mean consumers, are hungry for performance. So we don't demand the same resolution. No, we demand more resolution, higher resolution. I mean more bits, right? From 8 bits to 12 bits, or even to more than 20 bits for your ADC deck, blah, 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 all of them. Wow, the voltage becomes smaller and smaller, but we need to differentiate more and more levels, voltage levels. It is really hard to achieve. So it means what? The life for analog IC designer becomes harder and harder, right? However, if we convert the signal to time domain, there isn't any kind of limitation, the so-called hard limit. For you to differentiate, it's up to you. It's up to your application, right? If you cannot see all those time references clearly, then you can enlarge it to fit your application. For example, for bio application to sense our body temperature, our heart beat rate, blah, blah, blah. How fast you need to process all those biosignals? Usually kilohertz, the most, maybe 100 kilohertz, good enough. 100 kilos means what? Almost nothing, nothing. I mean, in speed, humankind enjoy it very much because for our electronics, 100 kilohertz means almost zero, almost DC level. Okay, you don't need to worry about the speed. You can be flexible to ease your own design, to simplify your own design. And the easiest way is to enlarge the time division, the difference between your timing references. That's it. And for voltage differentiation, you need op-amp. You need voltage comparator. And how about in time domain? You still need to compare the input signal and your timing references, right? Earlier or later, just like voltage signal, higher or lower, right? How to differentiate it? Very simple, with a D flip-flop. Good enough. Yeah, this is what you guys need to think by yourself. Today, I'm not your teacher. No, I'm only one of the invited speakers. So I cannot go to the button to help you explain everything in good enough detail. So think about it. Why you only need such kind of D flip-flop to differentiate your input and your reference timing signal. Which one is earlier? Which one is later? Think about it by yourself. Okay, and this is some kind of very complicated op-amp circuit. And for D flip-flop, this one is the simplest, but it is dynamic. Okay, if you would like to get some kind of static D flip-flop, please go back to reread your microelectronics. Yeah, it is already taught there. Okay, further, yeah. First of all, I would like to share, maybe you will be curious, how can we convert such kind of analog signal into time domain? For some applications, piece of cake. For example, for temperature sensing, to sense how high the temperature is, you can convert the temperature into time domain very easily. Why? In the past, actually, most of the designers, they converted temperature into voltage, then apply ADC to convert the voltage into digital signal for later processing. That's it. That is the traditional story. But we are different. Me and my students are different. Why? Because we cannot compete with them in such kind of voltage domain temperature sensing. They may, for example, Professor Kofi Martinwa from Delft University of Technology. He is one of my best friends around the globe. He focuses on such kind of temperature sensing for more than, I think, maybe 30, more than 3 decades, 30 years. How can we compete with him? No way, right? Till now, he's still the top one in the world for temperature sensor design. But we would still like to create something brandly new to compete with them, right? Not in accuracy, sorry, but in what? Cost, power consuming, chip area. Wow, we can make it even better than Kofi's design. So we need to convert. So from the beginning, we converted the temperature into time. Yeah, in brief, what is temperature? The operational definition is the vibration of your lattice, of your crystal, right? The higher temperature means the more vibration. Yeah, I think it is much easier for you guys to understand, right? So with higher vibration, what is the consequence? For free electrons, if they would like to flow from this direction to any kind of direction, the more vibration means what? The more collision of the crystal of the free electrons with the crystal, right? So the propagation will be lower. The propagation speed will become smaller. So what is the consequence? It needs more time for propagation. So the delay, yeah, actually for the circuit, usually it will get more delay according to higher temperature. That's it, no secret, right? So with such kind of mechanism, usually your circuit will operate slower, yeah, in higher temperature. That's it. That's it. Okay. So that is our secret, because time is limited. So allow me to show you the result. Okay. Yeah, and we figure out the other. Oh, okay, that is also a very good mechanism for you to understand. I myself am not created, so I found that the pulse, if you send a digital pulse, okay, from low to high, then back to low, or reversely, I don't care. Oh, okay, for such kind of pulse, if it goes through a delay line means what? A line composed of many delay cells, and the simplest delay cell actually is inverter. I think all of you know inverter. I mean, not gate, right? So if you connect many of the inverters in series, then you compose the simplest delay line. Okay, but okay, from here, from the input to the output, yeah, it takes time, right? So that is a so-called propagation delay. And again, keep this in mind: the higher temperature, the more delay you need to face. Yeah, that's it. And then if the NOT gates are not the same, I mean, according to their size, for example, this one is larger or smaller in between the others, then I need to warn you. The width of the pulse will be smaller, will be narrower or wider. It depends on the size of the cells. Okay, you can enlarge it, make it a little bit larger or a little bit smaller. Then the width of the pulse will become smaller or wider. That is what I call it. I was the first to find it, right? So I had the right to name it. So I call it pulse shrinking. The mechanism is called pulse shrinking. And right now, I told my student to apply such kind of pulse shrinking mechanism to design DPWM with FPGA, digital pulse width modulation with FPGA. Piece of cake, right? We can control. We try to control the size of the delay cell, then to control the pulse shrinking or expanding. Yeah, that's it. Okay, that is very good for our DPWM design. If you are interested, you can contact me or through your supervisor, just like Professor Trio or the others. Yeah, we can cooperate in such kind of hopefully very innovative and brand new design with FPGA. Okay, allow me to show this. Yeah, I converted the temperature into time, then I don't need ADC, right? Because I have only time, right? So I can count it. I need to apply something called time to digital converter, but the simplest one actually is counted 1 period, 2 periods, 3 periods, right? To make the timing signal into digital domain. Counter is the simplest time to digital converter, in brief, TDC. Anyway, that is my innovation. I converted the temperature into time, then digitize the time signal into digital output with the help of TDC, time to digital converter, instead of ADC. That's it. And you can see the chip size is the smallest on Earth when I created. And the performance is not so good, to be honest. The performance may be, according to error, I think mine is about 1 order larger. I mean, 10 times more than Coffee's design. But if you are talking about the power, the size of the chip, I promise you, we are 2 order better. Okay, so for accuracy, yeah, mine is 1 order less, but for the other performance, yeah, we are 2 order better. Briefly speaking, ours is easy because for theirs, their accuracy is less than 0.1 degree Celsius. That is too good to be true. For humankind, I think, especially for your daily lives, I think positive, negative 1 degree will be good enough. Okay. Anyway, anyhow, I and my supervisor published such kind of very simple design in the top 1 IC design journal, JSSC, yeah, Journal of Solid State Circuit. Since after me and my student created the other time domain application to publish the other 2, and along with maybe around 3 to 4 top 2 journals, okay, and maybe top 3, top 4 journals. Later, I will explain. Yeah, I will briefly discuss all of them. So that is the first secret I need to let you know. To convert any kind of analog signal into time domain, that's it. Okay, then you can use counter or the other TDC to get the digital output. That is what we need for FPGA analog applications. Then allow me to show you some of the successful FPGA analog applications. Anyway, anyhow, you can see analog signal and digital signal, they are totally different, right? If you compare their natures, their properties, nothing is the same. They belong to 2 different worlds, totally different. Okay, so even in such kind of voltage or current domain, you can see they are continuous for analog. Okay, for analog design, yeah, between the minimum and the maximum, it happens everywhere. For any kind of value between the top and the bottom, each value is possible. Okay, so it is continuous in this voltage or current domain. Yeah, and how about time domain? The same. It is continuous in both, in horizontal time domain or vertical voltage or current domain. And how about the digital signal? They are totally different, right? They are black and white. It means they have only 0 and 1, nothing in between 1 and 0. That is black and white, and we are colorful. Everything is possible. For them, only 2 values are possible. So we are different, totally different. However, allow me to point out that the signal in digital domain is still continuous in time domain. So this is the reason why I recommend you to convert your analog signal into time domain. Then we can do quantization in time domain with FPGA or the other kind of digital circuit. All right. So till now, there are quite many issues. Circuit can go from analog to digital. For example, time to digital converter, phase lock loop, delay lock loop, frequency synthesizer, many of them. All right. So the most important slogan on this slide is convention. Always means no innovation. Convention means what? Tradition. Tradition means what? No innovation. So hopefully through my talk today, especially the students had better think differently with the others. You create your own new ways for design. In the future, you will be much more successful than all the other traditional students. Okay. Yeah, in the past, FPGA, digital to digital, analog to analog, they are totally different. Okay, there is a clear cut between those two words, digital and analog world. But nowadays, for FPGA vendors, they push their circuit into analog domain for a little bit. Why? Because they embed ADC, DAC, PLL, DLL, many of the key analog blocks into FPGA, right? So they try their very best to push FPGA into analog domain. And we, FPGA analog designer, we push our circuit a little bit into digital domain. But why? How? Convert the analog signal into time domain. That's it. That's it. I may be the first or among the first to create such kind of brandly new idea, right? Convert the analog signal into time domain, then it can be processed with digital circuit or even with FPGA. So you can see there is some kind of overlap to make such kind of FPGA analog application possible. Okay, so is there anybody know this? What is the symbol? Anybody has any idea? What is this? Nobody. Okay, don't tell me that is Taiji. No, 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 it is not Taiji. It is not complete. Allow me to complete it. You need those two dots, right? Black in white, white in black. That is me and my student would like to be. To embed our analog thinking into digital domain or vice versa. To embed digital thinking into analog domain to complete the whole Taiji, to complete the whole world, right? And in this way, we can, or you also can be very, very outstanding, innovative, and successful. Okay. Yeah, we have many kind of FPGA applications. I have no time to discuss with all of you. On Earth right now, we have the two top companies. First of all, Altera, but it is bought by Intel already years ago. So right now we have Intel and Xilinx. Yeah. So for today, maybe I have only time to explain how can we achieve such kind of temperature sensor. In the past, that is some kind of analog design, but we realize it with FPGA. Okay, that is the first. Again, all those actually, they are digital circuit. Me and my student compose something called cyclic delay line. What's inside? I told you already. What's inside? Buffers. One buffer means what? Two inverters. That's it, right? So we have even number of inverters for such kind of delay line, and I make it cyclic. So it means what? I convert the temperature into a short pulse, right? Then feed the short pulse into such kind of cyclic delay line. So yeah, for such kind of, according to the temperature, as I told you, the higher temperature means the longer delay for such kind of delay line, right? So it means what? The period for such kind of circulation will become larger and larger and larger. That's it. And comparatively, we have another counter, driven by reference clock, especially from crystal oscillator. The period is fixed, right? So we create maybe, for example, 10 bits here to count our crystal oscillator. 10 bits means 1024 counts, right? So we count 1 and 2 and 3 with crystal oscillator. So we get a fixed time mask. Okay, within such kind of fixed duration, never mind how high or low the temperature is, according to crystal oscillator, the mask signal is fixed. Then we count how many times our cyclic delay line can circulate. Again, the higher temperature, the larger period. So for the fixed mask, less count you can get. That's it. Because the circulation time becomes larger. So for such kind of fixed mask, yeah, the counts, the number of circulation will be decreased. That's it. That's it. The higher temperature, the less count we can get for the output. Wow, that's it. Okay. If my explanation is too fast for some of you to get full understanding, no worries. You can Google my papers, then read it. You can get a much better understanding. Anyway, anyhow, allow me to show you the important figures. For such kind of very, very simple circuit, we only use 140 large elements, right? And then how about the error? Is about minus 1.5 to positive 0.8. Yeah, for 75-degree range, and the power is a little bit more than 8 microwatts. Now, this is a fully digital, not only fully digital, but also realized with FPGA. Okay, allow me to compare it with my own analog design here. Yeah, you can see how much is that? 10 megawatts, right? And the angle actually minus 0.7 to positive 0.9. Keep all those two figures in mind. Then let's go further. See? How about the result? For error, it is about doubled, okay? Less than 2 times larger than my previous design, okay? And how about the power? It is reduced, right? That is the first for humankind to implement such kind of analog temperature sensor with FPGA. Not only with digital circuit, but also with FPGA. That is the first, the very, very first for all humankind. It opens the door for not only us, but for all the other engineers, if they are good at digital design, especially with FPGA, they can try the same thing. They can try to create their own analog application with FPGA implementation. I hope me and my students can inspire all those talented digital designers to do the same thing, including you, my audience. Yeah. And allow me to show you, even interesting is that you can see, this is the FPGA board from Altera we used to implement such kind of innovative design. How much for such kind of FPGA board? To my calculation, about $200 NT. $200 NT instead of US dollars. Wow, it's really, really cheap, right? In that era, each board costed me around $7 US to publish a paper on top 2 IC design journal. IEEE transactions on circuit and system 1. Wow, not only one paper. No. We try to compete not only with ourselves, we try to enhance the circuit. So, if you go back to have a detailed look of such kind of circuit, cyclic delay actually is no good. Why? As I told you already, pulse shrinking, right? For the pulse, it will be shrunk or stretched, expanded according to the inhomogeneous delay cells. nothing will be the same. After fabrication, all the gates, not gates, or NAND gates, or buffers, I don't care. All of them won't be the same after fabrication. Each cell will be different. So according to the different cells after fabrication, the pulse needs to face pulse shrinking or stretching. The width will be reduced to 0 or expanded to saturate the output. No oscillation, no circulation. It's no good for our design. So the first thinking is to replace such kind of ridiculous cyclic delay line with oscillator. How to compose oscillator? Very simple. Add number of inverters connected in a cycle. That's it. As I mentioned already, here to be a cyclic delay line, we need even number of inverters, right? If I make it into odd number of inverters, then such kind of circular connection, connect the output back to the input. I promise you, it will oscillate after power on. That's it. Piece of cake. With oscillation, you don't need to face any, you don't need to worry about any kind of shrinking or stretching. Just forget about it. And then the second modification is, from the beginning, we have fixed number of periods from the crystal oscillator. So I told you the mask signal, the width of the mask signal is fixed, but I try to make it flexible, adjustable. By what? By what? Very easy. Yeah, for such kind of counting, how many counts you need from the crystal oscillator? We made it fixed in the past, but make it changeable. We need something called programmable counter, right? That's it. That's it. Only 2 modifications to make the cyclic delay line become oscillator with odd number of inverters equivalent, okay? And then make the fixed counting to be adjustable counting. That's it. That's it. Okay, that is our second design. And you can see, only 48 logic elements used. Oh, why we need such kind of flexible counting for crystal oscillator? We apply it for 1-point calibration. Okay, for detail, because time is limited. So anyway, anyhow, if you would like to go to the bottom to ask why with such kind of changeable, programmable counter, we can support 1-point calibration, please read my paper. Okay, it is also published on such kind of top 2 IC Design Journal, TCAS1, in 2011. I mean, for most of the ITB students, you are the most talented in your own country. You are the top of the top. On average, your IQ is better than my students. I'm not comparing you to the students from the from National Taiwan University. That is also the top of top in Taiwan. But even I compare you to NTU EE students in IQ, I guess yours is better, is higher. Why? Because your population is 11 times larger than us, right? You are the top of 11 times more population. On average, your IQ is much better than ours, right? So my students can create such kind of brilliant ideas for 2 versions. And since after we created the other kind of FPGA temperature sensors. Anyway, anyhow, even till now, I have 2 students focused temperature design, one with FPGA, one designed by himself. I mean, with analog design. Okay, that's it. We still design such kind of innovative temperature sensor. How about you? You are more talented than my students, right? If you are interested in paper publication and money making, do join us. I can introduce all of you to TSMC, MediaTek, Realtek, any kind of high-tech company here. From MediaTek, it promised that after graduation, even with master degree, you can make 2 million NT dollars divided by 28. Yeah, anyway, around 70,000 US dollars per year. Okay, with master degree. Think about it. You are more talented. You can create even more brilliant, innovative idea. I can help. Our professor can help. Your professors can help. We can have such kind of collaboration. Okay, let's go further. So finally, I can have some kind of very brief introduction to FPGA, time to digital converter. Hopefully to inspire all of you to create your own innovation. Okay, so as I mentioned, the simplest TDC, time to digital converter, to convert the time into digital output, the simplest is counter. For example, this is the input T in, right? You can count it. You can count its width, its duration by counter. 1 clock, 2 clock, 3 clock, piece of cake with excellent linearity, right? If the clock is ideal, then you don't have any kind of error, right? You have perfect linearity. So this is some kind of ideal timing diagram. However, again, we are humankind. We are not any kind of gods or goddesses. Sorry for that. So you need to face the ugly truth. Okay? That is some kind of practical timing. Your input cannot be synchronized with your clock. Never. Okay? Yeah. So you will have something wrong to the beginning and the end, right? You need to solve such kind of errors. With counter, T1 and T2 will become your error. All right. So how to reduce the error? Only one way, to reduce the clock period, T clock, to reduce it. But to reduce T clock, the period, the period of your reference clock, what does it mean? The smaller period means what? The higher frequency, right? So I told you how much accuracy or resolution we need for current TDC design to compete with all the others. 1 picosecond. 1 picosecond accordingly for the clock frequency. How much it take? Anybody has any idea? 1 terahertz instead of 1 giga. 1 gigahertz can only achieve 1 nanosecond resolution. Sorry for that. Too poor to compete with all the others. That is the worst on earth nowadays. Okay, nanosecond, forget about it. Too worse to be true. Okay? Too bad to be true. That is the worst. You need to enhance it for 3 orders. So from gigahertz all the way to terahertz. Oh, I promise you, no circuit on earth can operate at terahertz nowadays. No, nothing is possible. To the most, I guess, only tens of gigahertz. Yeah, maybe very few. You can count it by your own hands. Less than 5, I guess. 5 kinds, or even 0 kind of circuit can operate higher than 100 gigahertz. But I am talking about 1000 gigahertz, to achieve 1 picosecond resolution. Forget about it. Yeah. Even human can make it in the future. It means what? Huge power consumption to make it totally impractical. Nobody would like to use such kind of TDC. Too power hungry. It consumes too much power. Okay. So how to improve it? The next idea is delay line. You can see, yeah, you can feed the clock or your input through the delay line, then sampled by the others. Very simple idea. Look like this, right? This is your T in, and I feed the clock into delay line. So that is the first, the beginning. Then after the first stage, it is delayed. Then for the third stage, for the delay, blah, blah, blah. Then we can count 1, 1, 1, 1, 1, 0, 0, 0. Congratulations. You sum up how many ones here, you will know the width of your T-in, right? So what is the resolution? The resolution actually is the tau. And what is tau? Tau is the cell delay, the propagation time from the input to the output. That's it. Okay. Usually with good processes, yeah, just like 90 nanometer all the way to 5 or even 3 nanometers. How much is the cell delay? I guess for example, 0.80 micron, maybe you can make it tens of picoseconds. With 5 or 7 nanometers, I guess you can make it around 10 or a little bit less than 10, a few picoseconds, but it's still not good enough. Why? We need 1 picosecond. Okay, 1 picosecond, I think, is still mission impossible for even 3 nanometer process. It is under development for TSMC and Samsung. Okay, right now the best is about 4 nanometer process. So even in the near future, don't expect the cell delay will become 1 picosecond. Sorry for that. It is totally impossible. Okay. To make it even worse, I told you already, we are humankind. We need to face any kind of non-ideal effect. Nothing is ideal. Nothing is perfect. For all those delay cells, they won't be the same after fabrication. Okay, so the ugly truth, it is not beautiful. It's so ugly. The truth is so ugly. What is that? Oh, sorry. Taus won't be the same. Tau 1, Tau 2, Tau 3, Tau anything won't be exactly the same. So you need to face some kind of linearity error. Okay. Anyway, if you would like to enhance the resolution, allow me to show you. It is created by myself. Yeah. You can have delay wrapping. As you can see, for example, this is the first delay, then the second delay, then the third delay. Oh, if the delay is, and then all the way, right? Finally, if the delay line is long enough, then the delay, the accumulation of the delays from the first to the second, and finally, it will be one reference period, right? But according to such kind of periodicity, because the clock itself is periodic, right? So after the delays expands out of the period, it will be wrapped back. You can see from here back to there. See, for all those delay larger than 1 period, it will be wrapped back by wrapping. Okay, it will be wrapped back into the first reference period. So it means what? It means according to the same operation principle. Yeah, this is the original tau, right? Original delay. But after wrapping, you have many of the others after wrapping back to divide the T in with even better resolution. So allow me to show you. After wrapping, yeah, the delay, the phase between the rising edges of all the delayed clock, it becomes the resolution, just like delta tau. Where is tau? Right now, for such kind of example, tau becomes 2 delta tau, right? Tau is the cell delay here. Okay, for each cell, ideally, it gets tau for delay. But after wrapping, the effective resolution becomes delta tau. The delay, the timing difference between all the edges after wrapping, that's it. Okay, so delta tau becomes the effective resolution. We can make it even better. Yeah, we can make it even for 1 picosecond as you like. Yeah, again, there is no performance you cannot achieve. There is only some cost, yeah, some expense you cannot afford. That's it. So just pay for it. Pay higher price, higher cost to achieve better performance. All right. So what is the problem after delay wrapping? Again, don't expect after wrapping all those delta taus will be exactly the same. Sorry for that. So you can see equivalently, some of the after wrapping, some of the delays become smaller, some of the delay becomes larger, smaller, larger, smaller, blah, blah, blah. Sorry for that. Okay, why? Not only the cells, they create such kind of delta tau difference, but also the placement. Yeah, if you know digital IC design or you know FPGA design, you need to from the beginning you just write down the very low code to explain what you need, right? To describe what you need. Then the EDA tools, just like Quarters 2, Quarters Prime, anything, they can help you to compose the circuit. And after they compose the circuit, they need to place all the NAND gates, any of the gates inside the FPGA, and then connect all of them. We call it routing. Okay, so that is the result of auto placement. Wow, you can see, they spread randomly inside your FPGA. So the whiles between the delay cells, actually according to the auto placement, it causes a lot of delay variation, longer or shorter. The longer line means longer delay, larger delay, right? Okay, that's it. So me and my student would like to enhance the homogeneity, to make the delay as uniform as possible. What we can do, we do such kind of placement manually by our own hands instead of through the help of EDA. We have APR, automatic placement and routing, through Quarters 2. Yeah, the EDA tool for FPGA. Anyway, we can do it by ourselves for such kind of manually controlled placement, but nothing is free. You need to pay for it. My students need to write many of the programs to control the placement. We have STF file, right? A QSF, quarters setting file. Okay. If you would like to go to the button, please read our article. Okay, not only for such kind of assignment editor, but also for FPGA, they have blocks. The first cell, the second cell, the third cell inside the block. So the cell delay between the blocks becomes the shortest. However, the delay between blocks, they have boundary, right? So the routing will become longer. Oh, it is no good, right? So we try to do it very similar to this. See? Yeah, it means for all the delay lines, the first from the first block, then the second to the first of second block, to the third, to the first of the third block, blah, blah, blah. In this way, we can get the uniformity for delays. Got it? We place all the delay cells by ourselves and get rid of the boundaries, the effect, the longer delay impact among the boundaries of such kind of lab blocks. Okay. In brief, we try our very best to control the placement and routing. They have API, automatic placement and routing. No, we make it by our own hands. Okay. And also, we need to shorten our delay line. In brief, for 1 picosecond with 800 megahertz, the period is 1.25 nanosecond. It means 1,250 picoseconds. So how to make 1 picosecond resolution? The period is 1,250 picoseconds. So it means what? We need how many delta counts here? The same. To make it 1 picosecond for resolution, we need 1,250 delay cells, blah, 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 all of them. Okay. However, they are not homogeneous. They are not uniform, right? So we need more to be selected. That's it. Okay. For my students' design, maybe we select 1,000 from 8,000 or 4,000. I cannot remember that. Okay. To achieve the best linearity, the best uniformity, okay, for our delay lines, but it will become very long. According to Pershing, it doesn't make any sense, okay? The clock will be shrunk or expanded to 0 or 1, and to the final stages, you don't get any kind of clocks, all right? So we need to shorten it. How to shorten it? We can make such kind of two-dimensional delay line. So for example, if you need 4,000 to be selected, out of 4,000, you select 1,000 more, 1,200, blah, blah, blah. Okay, oh, that is too much, right? So we can make it how much? For example, 40 by 100. So totally, with such kind of two-dimensional delay line, we can create, again, 4,000 delays to be selected, right? But what is the longer path? From here to there, only 40 plus 100. So the length of the delay line is reduced from more than 4,000 or 8,000 all the way to how much? 40 plus 100. It is much shortened. We can make it even better with such kind of multiple delay lines. Yeah, 100, 100, 100. Why? No 40, because the wires to connect your clock or input to all the delay lines, they need to face difference. Okay, a lot of difference between the delays from the same clock to different delay lines. So in this way, we don't need this. You can connect all those delay lines, small delay lines, in parallel equivalently. You can compose the same number of delays to be selected. So now the longest path is from here to the end, right? 100, as I mentioned, 40 by 100, something like that. Okay. Yeah. Anyway, anyhow, that is what I can help. According to the time limit, allow me to show you the result. Okay. Yeah, that is the overall structure. Yeah. And even for measurement, we need to spend a lot of time. So my talented student helped me to set up such kind of automatic measurement environment through the help of Sequelix. Okay, what is that? Google it by yourself. Okay, that is some kind of automatic test equipment tool, some kind of script. You write the scripts to control your computers. Then you can synchronize all the equipments, okay, through the help of Sequelix. That's it. So my student just click the button of the start button of Sequelix, then go back to sleep. Then for next morning, he or she comes back to collect the final data. That's it. That's it. In the past, they need to wait. They need to do it by their own hands for many hours or even for many days. But right now, only one click. Yeah. After that, everything will be finished automatically. Yeah. Anyway, that is some kind of result for 1 picosecond. You can see the short range measurement for StrateX4. You can see the linearity error is less than 2. Okay, and how about Cyclone 4, the older version? Okay, with 1 picosecond, you can see resolution. Okay, then the angle, the error is less, right? And how about the long range? From 100 picosecond to 1 microsecond. This is again for StrateX4. The error is a little bit larger than 2.5, positive, negative. Okay, picoseconds, because 1 error is means 1 picosecond. Right. Okay. So in brief, the only worst performance for Cyclone 4 is the IMS resolution. Yeah, because according to jitter, blah blah blah. Yeah, even the input is fixed, the output is still changeable. It's variable, right? So the smaller deviation, the better accuracy. Okay, so for the old, for the new chip StrateX4, it is much better in IMS resolution. That's it. So compare both of two and compare with all the others. In brief, we achieve almost the best resolution among the best. But for our linearity, we are the best. Okay, for INL, you can see many of them. You can see. Okay, we are almost the best. And the paper is submitted to the ITB transactions on instrumentation and measurements. Yeah. So we try our very best to revise the paper. Yeah, we get some kind of very similar to major revision. Anyway, anyhow, for future work, we would like to enhance, to reduce the IMS resolution and to reduce the logic utilization. Yeah, I know how to do, but it's some kind of secret to protect my students. Okay, and for all the others, sorry for that. I don't have enough time, so go back to this. Yeah. Key requirement to success for all of you. IQ is not everything. EQ is more important for analog design. Okay. So anyway, you need hardworking, and hardworking, right? Thanks for your attention.
Thank you very much for outstanding inspirations, Professor Poki. Now we have several questions here in the chat box. The first one is from Mr. Budi Nugroho. Their host, the time domain term here, I think, different from my conventional definition of time time domain signal, right? That's the,
Yes, yes.
so what is the difference?
In brief, because time is limited. Sorry for that. I'm too talkative. Anyway, I think the major difference is I embed the analog information into time signal. That's it. Okay, that is the most important difference between the traditional timing signal and my own. For traditional timing signal, I don't think they have any kind of analog information inside. But for our design, all those timing signals they have.
Okay, thank you. We will move to the second question, Prof. Poki.
Yep.
I have simple curiosity questions because I don't have knowledge in IC design. I just wonder if using FPGA, general or your new approach, can we create a system with a very small scale, such as implantable chip or drug delivery chip for biomedical applications? How about the issue on power, noise, and signal processing accuracy when developing a system on such tiny scale?
Oh, that is a really good question. Hard to answer, but I can try my very best. Anyway, with FPGA, for such kind of analog design, actually you can see it as some kind of concept proving, right? You can prove your analog concept with such kind of FPGA design. And you can see for my first two examples, we used very small chips, very inexpensive, very cheap FPGA chip, right? With how many gates? From the beginning, 140 to the end. For the second version, only 48 logic gates. So you can get, if you would like to fabricate your own chip, the size is so small, right? To fit your biomedical applications. And according to the power consumption, I promise you, less than 100, only a few tens of large gates, the power consumption, I think it's totally possible to be smaller than 1 microwatt, or even you can make it according to narrow watts or tens of narrow watts. Piece of cake, I promise you. I mentioned already for my two students, one lady and one boy, they focus on FPGA temperature sensor design. The other one is analog temperature sensor design. My own expectation is very smaller chip size, very cheap, and very small power consumption. How small? My target is less than 1 microwatt. Okay. Do I answer your question? Hopefully.
Yeah, is it answered, Mr. Isa?
Yeah, thank you very much, Professor Poki.
Yeah, no worries. We can help each other. If you would like to make something, have your chip fabricated, do join us. Now we can help each other.
He is a lecturer in biomedical program in electrical engineering.
Yeah. Everybody is welcome to join us. I'm talking about the collaboration research project between ITB and NTUST, right?
Yeah.
Okay. Next.
Thank you.
Okay, thank you. Maybe we will move to the next question. Prof. Poki, is there any tutorial source paper to which we can learn further about how the temperature to time converter works? Because I'm interested about how you utilize the FF and crystal oscillator for that from Mr. Christian.
That is an easy question for me because I created all those ideas for my students. The simplest answer is you can Google online or search my papers through IEEE Explorer. That's it. Yeah.
In
If not,
journal,
you just
journal
write
first
me.
step, right?
Yeah, you just write me an email. I will download the paper for you. Okay, that's it.
Okay, thank you. Is there any questions? Maybe I have one questions. How about
Please.
the high frequency such as wireless communication? Is it possible to do the time domain conversion?
Oh, that is the hardest question I get today. I guess Professor Trio will provide you much better answer than myself, because I don't touch such kind of very complicated digital design. Yeah. So
Okay.
hopefully you can get the right answer from Professor Trio.
Okay, thank you very much.
Trio, can you help me to answer this question?
Maybe the sensor is very, very fast. I don't know.
Oh,
yeah.
Anyway, if you would like to sense the operation temperature of your 5G chip or circuit, oh, definitely, you can implement it inside FPGA, no worries. Right now, I have an international cooperation project with a Czech Technical University in Prague, also between CTU and NTUST, right? I got one project with CTU and the other project with Kyushu Technical University. Yeah. Anyway, anyhow, all focus on with Kyushu Tech for FPGA analog design, and with CTU, that is for temperature sensor. Yeah.
Okay.
Maybe I have a comment
Posing.
and another question from Professor Poki.
Please go ahead.
So it means in the case of radio, so you mean RF. So we need to make RF to time domain signal, isn't it? Time domain pulse. Yeah. So it's been, but the RF itself is still in voltage. Yeah. So it means we have to make something like a ADC, but not to parallel digital, but to time. Yeah. So it's work a little bit similar with the ADC. Is it correct? I just to make sure.
Yeah. Anyway, according to Trio's comment, I highlighted already from the beginning. Many of the key analog blocks already embedded in FPGA chips. So you can have ADC, I told you that if you would like to process the signal directly, then you need to convert it into time domain, right? But if you would like to process it indirectly, then you can use the embedded ADC or the others to convert your RF signal into digital domain instead of time domain, into digital domain. Then your digital circuit can process it, yeah, all the way. No worries.
So I mean,
comment.
I mean, my question is basic. I mean, if we have the signal already in the voltage, which one is better, in time domain or in time domain or in parallel, like ADC?
I only guess. Usually, if you focus on performance, on, for example, accuracy, operation, speed, right? Then in voltage domain should be better. There are only very few cases we can make it in time domain with better performance than in voltage domain. Yeah.
Okay.
Yeah, hopefully I answer your question.
Okay. And then in order to adopt this the system in large deployments, so we need someone to create many sensors that output in time domain. Is it correct?
Yeah, if you would like to make it fully in digital domain, I mean with FPGA or not, yes, definitely you need. Okay, but again, that is the logic thinking is to directly or indirectly process all those signals sensed, all those signals from the sensors. Yeah.
Okay. Okay. Thank you very much, Professor Poki.
Welcome.
Okay,
My
thank
pleasure.
you. I think this is already the time. Maybe Professor Trio have some closing remarks.
Okay, thank you very much, Professor
student.
Poki, for your nice presentation. We would like to thanks for your presentation and giving inspiration for innovation for us this morning. Yeah, I hope in the future we and also the students can collaborate with you. Yeah.
Yeah. My much honored pleasure.
Okay, thank you. I think that's all for me. Thank you.
Okay, thank you very much. We can give some applause for Professor Poki.
Maybe
And
taking picture together, maybe.
Yeah.
Okay, maybe taking picture together. Maybe first, Professor Poki can stop the share screen.
Yep.
Yeah.
Okay. Thank you all. Bye.
Okay, and then I will give some comment. The first page, 1, 2, 3. Okay, thank you. The second page, 1, 2, 3.
Please open your camera.
Please open your camera and smile. Okay, the third page.
Mungkin diulang lagi nanti. Ini kayak tadi kameranya pada tutup.
Iya, pada tutup ya. Okay, from the first page ya. Okay. 1, 2, 3. Nice.
Please thumbs up.
Yeah, thumb up.
Yeah, that is a very good webinar.
Yeah, the third page.
True.
Okay.
You didn't thumb up. I cannot see your thumb.
Okay.
Yeah.
Okay, I think it's all and finished. Thank you again, Prof. Poki. Hopefully, in the next occasion, we can collaborate more and involve many students from ITB. Here also, Mr. Mervin from our groups also attend, and also Mr. Nur Ahmadi and Mr. Nana. And thank you, and goodbye. See you.
Bye.
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 Thank you, Professor
Thank you, Prof.
Poki.
Thank you, Prof.
Yeah.
Bye.
My much honored pleasure.
Thank you, Mr.
Thank you.
Thank you, Prof. Poki.
Terima kasih.
Excellent. Sama-sama.
Sami-sami.